Hey there, in this video I'm going to talk about the discrete Fourier transform. And the purpose of the discrete Fourier transform is when we're in the land of arrays and we have a set of numbers, we don't really have a continuous function. We have something like y is an array that might be created by some kind of function, but we may not know what the analytic form of that function is. You know, like this might be data coming out of a file. We don't have a function, we just have data. And we're going to say that it has n elements. And we're going to see the length of the array does matter here. So if we tried to do a continuous Fourier transform, we're going to run into a problem right away. And that problem is we have to do an integration with an f of x, and we don't actually have an f of x. Now you might be tempted to do something like, say, a trapezoid roll integration, and as it turns out, if you do trapezoid roll, you'll get exactly the same result that I'm about to get. But the reason for that's not really all that obvious. But so for now, like this approach just doesn't work. So I want to do something that's like a Fourier transform, but I can't do it the continuous style. So what we're going to do is we're going to go back to the Fourier series. And if we think about, what was our definition for the Fourier series? It says we can take any function, and then we can write it as a sum of infinite number of terms, each of which are periodic, some kind of coefficient each. And each of those coefficients is found by integrating. Okay, so we're going to make some changes. If we think about what's going to happen here is we can't really integrate anymore if f of x is basically an array. So we're going to have to change the integration into a sum. So in this regards, it's kind of like the opposite of how we derive the continuous version. So here we're going integral to sum. Also, we're going to let L here be half of our array's length. So the idea here is if we go from negative L to L, that's a complete period. And we're saying, if we're doing a Fourier transform, we're saying suppose that over the entire range of the array, this is one of those so-called periods. And we pretend, or we hope, we trust that the array then repeats itself in principle beyond its bounds. Okay, so if the entire range is negative L to L, that means that half the array is going to be L. And so with those substitutions, we can write a new version of gamma k. Gamma k would be equal to 1 on n. And then instead of integrating, we're going to sum. Little n will be the element of the array. We have to go from the beginning, which is 0, to the end, which is n minus 1. And then in there, we put the nth element of the array y. So remember, y in principle contains the function f of x, just not in a continuous sort of way. And then we have the exponential, and that part hasn't really changed other than we've changed what L is. So we're going to have a negative I here, and then we're going to get 2 pi kn divided by capital N. So I still have k here. I have k and n. K giving us, right here, k here giving us the kth element of gamma. So basically now gamma is an array. Now the actual conventional definition is a little bit different. And by conventional, like just about everybody uses that. And the difference is, what do we do with this factor of n? You remember when I talked about continuous Fourier transforms, we had that factor out front, which was kind of arbitrary, whether it was attached to the Fourier transform or the inverse Fourier transform. And as it sort of happens historically, it's kind of backwards here with the discrete Fourier transform. So the conventional definition is to call the array C, so C sub k, and that is by definition n times the value gamma we just found. And so if we multiply everything through by n, basically get rid of the coefficient out front, then we're going to have our basically universally accepted definition of a discrete Fourier transform. We're going to sum over the entire array, y, and for each of those elements, we're going to multiply it by the complex exponential that has a negative I, 2 pi, n, divide that by the total length of the array. And likewise, we can find the, so this is the DFT. And likewise, we can find the inverse DFT. That's the original YK, but based on the C's, here we're going to have a 1 on n, basically, where you are moving this coefficient from the transform to the inverse. So it shows up here now in the inverse. And then we sum k here equals 0 to n minus 1. We're going to take the CKs and multiply them by the exponential with a positive I, 2 pi kn on capital N. So notice our summation variables are different here. For the DFT, that's this one up here, we're summing over n's, and for the IDFT, we're summing over the k's. So it's kind of like the difference between the in the continuous transforms, we were integrating with respect to x versus integrating with respect to omega. So same kind of idea. And the really cool thing about the discrete Fourier transform is that it is guaranteed to be completely reversible. So if you Fourier transform something discretely and then inverse transform it, you get exactly the same result back. This is an exact relationship limited only by rounding error. So that's what makes it so great for computers. Okay, so let's look at the discrete Fourier transform. So for our example, let's use the function we did in the continuous Fourier transform video. So that was equal to x when the absolute value of x is less than 1, 0 otherwise. And just as a reminder, this is what we got as our continuous solution. So this is just us plotting the analytical formula for it. And we found that the coefficients are all imaginary in this case. And when we plot their magnitude, we have this sort of like mirror image double peak kind of thing. And getting this mirror image effect is what you always have happen if you are transforming a real function. So if your function was real to begin with, all of the coefficients, all the positive coefficients are complex conjugates of all the negatives. And so when you plot the magnitudes, they're mirror images. Okay, so I want to start out first of all by making an array that holds something that is basically our function, or really a subset of our function. Our actual function goes from negative infinity to positive infinity. Our array can't do that, so it's going to be kind of a sort of mockery of the original function. Let's give it 100 points, and we can change the number of points in it later on just to see what that does. And to make a plot, I'm going to need to do a linspace of x values. Let's go from -2 to 2. We'll do n steps. And then now our y values. Our y values are mostly 0. So we'll build it with the zeros, and then we're going to change the middle of the y array so that it is equal to x. So basically, if we look at our function definition up here, wherever the absolute value of x is less than 1, we want to make it x. Okay? So y at any place where the absolute value of x is less than 1 is going to be set to x in that same place. So x where the absolute value of x is less than 1. It might be tempting just to say is equal to x here on the right-hand side, but that won't work. The arrays have to be the same size. And then let's just make sure that that worked. So we're going to plot x and y. And sure enough, that's our shape. Cut off here at -2 and 2, rather than letting it go to infinity. Okay, so now let's calculate our discrete Fourier transform. So a discrete Fourier transform here is going to be based on a sum. We can really exploit arrays here to help us out. So C is going to be where we store our values. And the way I'm going to write this code is with a for loop. You'd have to have at least one for loop because you're basically summing in over 2 indices. And I'm going to start with it being equal to zeros, but I'm going to fill it in. So it could be anything to start at all. I could make it zeros, I can make it 1. There's even a function here called empty. And the way empty works is it just sets aside some memory on your computer without setting it to any particular value. But I'm going to set it all to zeros. And I want to make sure that I tell Python that this is a complex array, because in general, these coefficients are complex numbers. And otherwise, I'd be throwing away half my information. Okay, so n here is also going to be an array. It's an array of counters going from 0 up to capital N minus 1. So that's the same thing as just saying a range n. And then what I'm going to do here is I'm going to loop over different k values to fill in the array C. So each element of C is itself a summation of arrays. And since it's a summation of arrays is why we have to do this for loop. I know it'd be beautiful if it would all happen at once, and if you can figure out how, you know, please tell me. But you know, since we're summing things, I think we have to use a for loop. Anyway, in here we're going to have basically what we wrote down by hand here. So that's going to be y times exponential negative I times 2 pi. So actually, since it's times 2 pi, let's just make it negative 2j. Apply that by pi times k times n. Divide all that by capital N. So notice here that this lowercase n is an array. That's why we have this sum here, and we're summing over all these different lowercase n's. Everything else in here is a constant. The for loop will give us different values of k, which will then fill in different elements of the array C. Okay, so this code here should do the discrete Fourier transform. It's really just set some stuff up, do a for loop. And then let's plot it. So I'm going to go here with sort of a side-by-side like I did in an earlier video. So I'm going to put the real and imaginary components on the left and then the magnitude on the right. So that all can fit, I'm going to make my figure wider. I'm going to go 12 by 4, I think looks good. And then a subplot, 1 row, 2 columns, plot number 1. And there I'm going to plot the imaginary part of C. And let's call it imaginary. That'll be the blue line. And then I'll plot the real part. You'll notice I don't have any x values as I type these plot functions out. And that's because I'm just plotting element by element. What are the elements of C is what I'm plotting here. Okay, and then we'll plot the real ones with the label real. We'll need to show a legend. Oh, need to hit enter. Well, it makes me a little concerned that there was an error message, invalid syntax. Oh, we're gonna have to go back and fix that. Mad about up here anyway for k range. Oh, for k in range. Okay, so caught an error I was not even expecting. Anyway, I never finished making my subplots. So 1 row, 2 columns, graph number 2, and we here are going to plot the absolute value of C. We'll make it as similar to the previous graph as possible. So I'm going to make it a red line, and I'll give it the label magnitude. Show a legend and show the whole thing. Something else is mad. Module numpy has no attribute 0. No, it doesn't because they're called zeros. Now what? Fig size. How you spell fig size. All right. So here we go. Here's our plot. Now, this looks kind of the same, kind of different. It looks inside out. So if we compare that to what we get analytically, we have our peaks in the middle, right? So we sort of like start at 0 and then we drop down. And if we look here, if we start at 0 and we drop down, then we come back up. So what effectively happens when you do the discrete Fourier transform is, if you think about how your values are stored in an array, you don't have negative elements in your array. Like if you think about, like, say I have some array A, right? And I put in like -5, like where is -5? Well, actually the way Python would do it is it would count from the right. It would count inwards 5 from the right. And in some sense, this is a coincidence, but in some sense, that's what's happening here when you do a discrete Fourier transform. So these are kind of like, this whole right-hand side of the graph is kind of like analogous to the negative values here, or the negative k's here. And you see the same sort of thing here happening with the individual coefficients. You also notice we do have real and imaginary parts this time. It's not a pure function like it was last time. And that's because we don't have a continuous function. We have real, we have actual values in here. So when we do our discrete Fourier transform, we do tend to get a mix of real and imaginary values inside of it. But again, usually we're going to look at the magnitude of these things, and you can see it's got the same sort of shape that we had before. Now, some of this is kind of coincidence. You'll notice this goes -50 to 50, and here I chose to have 100 elements, so we have sort of like the same number of values in some sense, the same sort of range. But I could pick other values here. So like, what if I do 60 and I regenerate? Like, the array pretty much looks the same. It's a little bit less sharp right here. But regenerate my graphs. You can see like the spacing here has changed between the peaks and the valleys. It's got the same kind of character as the discrete transform, but it's not exactly the same. Discrete transforms and continuous transforms are not the same operation. So they are not going to be exactly the same. There will be similarities, but they are not identical. Okay, so what we're going to look at next here is how do we undo what we've just done here? How do we do the inverse transformation? So let me copy my discrete transformation code and let's turn this into the inverse. Okay, so what do I want to change? Well, first of all, I don't want to build an array C anymore. I want to make an array Y. Let's call it Y2, just because we don't want to clobber the original array. But we can start with it being zeros. We're going to fill them in. That's fine. We're not going to count over lowercase n anymore, but we're going to count over k. And then in our for loop, we're going to go over lowercase n, and we're going to fill in y2 of n. And then the function in here should be pretty similar, except instead of y, we'd use c, and we want a positive power for our exponential. But the rest of it will stay the same. So notice now that k here, let me get the highlighter going. K here is an array, and n is discrete values. But you know, it's very, very similar looking code. And so now we should be able to make a plot. So let's plot, this is the original y. We'll do it as black dots. And we'll just label it original. And then let's plot our new value y2 on top. Now this is complex, right? So it's going to be kind of mad when I try to plot it. It's going to yell at me. And what it does by default is it only plots the real part, but I'll get an error message or a warning message if I try to do that. So it's a little bit better to be explicit here. So I'm going to explicitly just plot the real part of y2. Because, you know, if we are undoing our Fourier transform, we are supposed to get the original function back. So it shouldn't have any imaginary component. Feel free to check that if you want, but you should find it's just 0. Okay, anyway, if we plot this out, oh no, it's mad about something. Oh, there's something going on weird here with my scaling. You know what? I forgot. It's like it's 60 times too big. It's like I forgot to multiply by 1 on n, which I'm supposed to, because that is in the definition. All right, don't forget that part. Well, all right. So here we go. We can see that we got back exactly the original values. And in fact, if we make this, let's make it dots, big dots, we should find out that we hit them piece for piece. Let's just switch the order of these just so that you're hiding the original. So we'll draw the big dots first, and then we'll draw the little dots, hopefully right on top, right on the middle. There we go. Right on top, right in the middle. So we get back exactly the values we put in. That is the one really nice thing about a discrete Fourier transform, is it's non-destructive. So we get back exactly what we had going into it. Okay, so in a follow-up video, really a follow-up lecture, we're going to look at this weird business here with the front being the same as the back in the array, like what's going on there.